Now let's see how J.J. Thomson and his team used all of these experiments. Again, we have a magnetic field and an electric field operating on these charged particles. And they found a very interesting property. First of all, they balanced the electric and magnetic fields. So you've got the electric field here, the magnetic field here, and you have the charged particles going straight through the tube. This enabled them to calculate the velocity of the particles as we showed on previous slides. Then they turned off the electric field. The particles were now deflected downwards because only the magnetic field is operating, and they hit a semicircular orbit and struck the side of the tube. So you're striking it somewhere down here. Once they found these particles in a semicircular orbit, they would see where it would make the screen fluoresce, and they would measure the radius of that semicircular orbit. Now we're going to go all the way back to Newton again, use his second law, and from that we're going to find out the ratio of the charge of these particles to their mass. Recall, the particles had a velocity which was equal to the ratio of the electric and magnetic fields. That would enable the particles to go straight through, and then they would be bent by the magnetic field. Remember, the electric field was turned off at this point. We now have the magnetic field exerting a perpendicular force. Now, we know what happens when you have a particle with a velocity and you have a perpendicular force exerted on it. It goes into a circular orbit, hence the semicircle that the experimentalists observed. We take Newton's second law, F equals ma. We now have a circular orbit, so we have centripetal acceleration, so A is equal to v squared over r. We know the magnetic force is qvb. We set that equal to mv squared over r. We do a little bit of algebra. We then substitute in the values for the electric field, which we know because we set it. The magnetic field was set, and r was measured by where the fluorescence occurred inside the tube. And after you calculate everything, you find out that the charge to mass ratio for these particles is 1.76 times 10 to the 11th coulombs per kilogram. This experiment showed that the particle had a very low mass for its charge. In fact, its mass per charge was 1,800 times less than the previous lowest amount measured for a particle, which people had been calling the hydrogen atom. And because that was, at the time, the smallest mass people found, they figured that was the smallest fundamental particle. However, we now have a particle that's 1,800 times in mass less than that. This led Thomson to propose that these negatively charged particles were something new, and he actually called them corpuscles. The name electron was taken from George Johnstone Stoney's work in 1874, and again by George Fitzgerald, who proposed it a little later, and that name stuck. Furthermore, since the electron was so much lighter than the hydrogen atom, it was concluded that it must be part of an atom, so there was some underlying structure here to the atom that had not previously been seen.